last week actually probabilistic perception, and we learn based off the project. If the project is, for example, stochastic or is actually deterministic, or if it's structured or atomic, or you have enough data or don't have data, you can choose which method of perception or learning you can use. And we already learned about neural network and deep neural network and convolutional neural network that make decision based on data-driven methods. The problem with them was when data is not good, decision is not good, and also is not explainable, also have problem of overfitting. That was the problem that we always have with data-driven methods like neural network. Explainability is another issue. From last class, we started talking one new method of perception that is explainable. And it's all based off math. You can explain it. If you get result, you can prove it that this is correct. We want to talk about that. We started talking about some basic element that you need for this kind of perception, like probability. We're going to continue today a couple of more, and the main rule that we're going to talk about, that is Bayes rule, and then going for Bayesian inference. That's the main thing, you know. If we learn Bayesian inference, means we know Kalman filter, how Kalman filter works, or any other filters, Bayesian filters, how they work. We can learn, for example, how ISAM works, and most of methods, advanced methods. These methods are advanced, but not difficult. They are not difficult. I try to teach them in a very a way that everybody understand, and in a practical way with hand-on project. I'm gonna make for each part some small project to learn that. If you can learn these parts, you're gonna be one step ahead of others. I'm sure about that. Okay, so let's see what is Bayesian inference, and first of all, we need to see what is Bayesian rule. Okay, before Bayes rule, we need to know product rule, because that's it. The last class we talked about joint probability when we have more than one random variables. We can make joint probability. So when we say probability of x and y, then x and y are actually random variables. Probability of x and y is joint probability. So what is random variable? Random variable is a kind of variable that has a distribution. It's not certain. It has some distribution. Like, for example, Gaussian, it has some mean and variance or covariance when it's a multivariant, when it's like a vector shape. So this is a joint probability that we learn. But joint probability can be written as a product of two things. You can say probability of x and y is given to probability of x, for example, multiply probability of y given x. So this rule called product rule. You can write this different way because probability of x and y and x are equal. You can also write P of y, P of x given y. So what that means, probability of y and x is probability of knowing, for example, one of them, like y, and then we know y, We just based off knowing y, we find probability of x. Probability of x given y means we already know y. So from this, you can get something interesting. These two are equal. If you put them equal, what we're going to get? We're going to get P of x is equal, P of x multiply P of y given x is equal to P of y, P of x given y. So you found some relationship between P of y given x and P of x given y. And this is the basic of Bayes' rule that we're going to see that next slide. I just wanted to show you here how these connections created. Probability of something given something is equal, there is a relationship, or there is some formula between these two. So we're going to see that, and that's the Bayes rule next slide. Okay, let's clean this up. So that's coming from product rule. So product rule is important. But what about if you have more than two variables, joint variables? If you have more than two joint variables, it still is possible. For example, if we have three variables, in that case, we call that chain rule. From product rule that was just two variables, we can go for chain rule. Chain rule saying if you have more than two variables, and still this rule exists. So we can say, for example, probability of x1, x2, x3 is equal to, we can factorize it. This is called factorization. Factorization is very, very important in probabilistic because it makes the problem simple. Makes the problem so simple. Especially if these probabilities are, do you have a question? Especially if these probabilities are the family of exponential. Why this is important to make factorization? Because if you want to find, maximize or minimize of this probability, and make optimization problem from a probability, if they are exponential and if they are factorized, you can easily get log. When you get log from exponential, this exponential and multiplication becomes addition, and exponential disappear because exponential and log cancel out each other. So that's why factorizations are very important. Later on, we can see factor graph. That is the last part of this class that we're going to teach you how you can use factor graph to do this kind of problems much easier. You know, factor graph is the ultimate part of perception that we're going to see, and is a basic for actually SLAM, simultaneous localization and mapping. It's based on factor graph. And so this is called chain rule. How it works, let me explain. Let me clean this up. So P of x1, x2, x3 can be written as P of x1. So if we know x1, we can find x2 based off that. x2 given x1 and x3 based off given x1 and x2, because we know x1 and x2 right now. It's coming here. However, you can write this to so many different ways. You can start from, because P of x1, x2, x3 is equal to P of x2, x1, x3 is equal to P of x3, x1, x. You can write it in a three-factorial way. So it's this is not just you can write it different way. The way that I did with join x and y, you can do with this as well. So this is called chain rule. So chain rule showing you how you can factorize joint probability. And joint probability is complex because it has actually dependency, showing dependency. We want to get rid of dependency. Dependency is always problem between random variables. And dependency is always problem. You know, you need to factorize to get rid of this dependency. And modeling dependency is one of the hardest things in on the wall, everywhere, you know. And modeling that is very complex. I'm working in dependency for a long time. When you are talking collaborating systems, when they are helping each other, it's not just helping, sometimes against each other. Sometimes two teams fighting with each other. They need to, it's not always helping. Sometimes they are acting to actually competing each other. That's another part. So that's all connected to dependency between random variables. They are all random variables. Okay, so this is the general way. Let me clean this up. So in general way, we can write something like that. We can say P of x1 to xn is the product of P of xi, x1 to I minus 1, and repeat it. Okay, so this was product rule and chain rule, that they are the base of this one. This is the main thing that we need to know. Bayes rule. So this is him. Bayes actually Thomas Bayes is Thomas Bayes is a British mathematician. 1701 to 1761, just 6 years, very short. But he did amazing. He did amazing job regarding what we know right now as AI or machine learning is all based off his work. You know, 3 scientists in terms of robotics, AI, and computer, they did amazing job. First one was actually Newton. That was before. And then Bayes. And who else? Anybody can guess? Isaac, Newton, Thomas, Bayes. Anybody else? That is very famous in terms of robotics and AI and machine learning. Gaussian coming like least square. It's coming based off Gauss. Carl Gauss. After these people, 1777 till 1855. Thomas Bayes is in this time, and Newton was the first one. That most of the dynamic, but they all were living like 80 years, but Thomas Bayes just 6 years, very short period, unfortunately. Let's write these two, 71 to 1761. So these 3 mathematicians or scientists, they did amazing progress and job in terms of what we know right now in terms of robotics and computer and AI, and so many other applications are based off this knowledge that they developed in that time, many years ago. So the Newton is like based off the dynamic and motion, law of motion are all based off Newton, that we are most of the cars, autonomous cars, and based off that. And Bayes is actually, Bayesian inference is based off that. Bayesian inference means you actually find probability of some unknown, like some hypothesis based off the data that's observing. That's amazing things. It's all based off whatever we are talking right now is based off that. And actually Gauss, the Gaussian distribution and all optimization coming based off his knowledge and his things. And least square, for example, is one of them that he developed in between 1777 to 18, but it was the last one. So yes, whatever we have right now is coming from these three people, most of them, at least the base was from them. And what we want to talk today is based off Bayes things. Okay, so let's clean this up. So what Bayes saying, or Bayesian rule saying, it said how we can update or believe about a hypothesis. If we have a hypothesis like H, if you believe something, if you believe the robot is here, based off some evidence, we can find that. We can find probability of that hypothesis. So we can find probability of hypothesis H based off some evidence E is equal to actually likelihood of that evidence and multiply to prior prior like that. Prior info. We have some prior info, probability of that prior. Probability of that prior, for example, for a robot is from the before and the speed that had before. You can estimate what is this position. Like, if imagine the hypothesis that I have is I want to actually find probability of this belief that I am in X and Y based off, imagine I'm a robot, and I was in X K minus 1 1 second ago, and I was moving with the speed of VK, for example, so I can find prior info about this. I also have some likelihood based off the new measurements that coming. For example, I know my distance to that wall is this much. So that measurements also help me. And this part is just for normalization. P of E is just for normalization because its probability need to be between 0 and 1. So we don't care about that part. Why we don't care about that part? Any idea? Because it doesn't have hypothesis on it. When we do optimization, we want to maximize and minimize that one, and we just consider the top part because we just look at the proportion of that. P of H given E is proportion of P of E given hypothesis multiply P of hypothesis. So that's the main point. When we do maximization and minimization, that part that doesn't have hypothesis is going to get out. We don't need that. So these two important. One called likelihood and one called prior. Okay, that's very important. So this is the basic of Bayes rule. So with Bayes rule, you can find this probability. And this probability, you just need to maximize it or minimize it to find unknown. What is unknown here? Hypothesis. The belief. You believe something based off new information that coming. that likelihood, and based off previous information, that is prior information. And this is the basic for almost most of algorithms that we know before, like Kalman filter is based off that. Particle filter is based off that. And any other Bayesian filters. Bayesian filters means working with these methods. Islam is based off that. And so many other applications. So let's see if we can understand this in this remaining time. Okay, so let's talk about inference. What is inference? So we have probability of some unknown given some measurements. Inference means get out information, get out X from this probability. So inference means actually finding latent variable. This unknown variable called latent. Finding latent variable. Because it's not there. Why we call it latent? Because this robot was in xk minus 1 before, but right now is xk. But we don't know where is xk. We just know noisy IMU, we know information from GPS, we know they are all noisy. They are not precise. They are not good enough for us to give. So that's why finding x considered a latent variable, not observable variable. We want to observe it. Finding that called inference. So inference means finding something that is not observable or is not precise enough. We want to find that. That's called inference. Most of the time, for example, position it can infer from the measurements, like a map, landmarks. Sometimes you have some landmarkings. You need to find their position or the map or velocity or bias or any environmental features can be inferenced. So sensors are noisy. Sensors are noisy. That's why even GPS that's supposed to give you exact position is not always precise. IMU drift, lidar range has noise, wheels slip, and cameras has distortion. So because of that, we need to infer. Based of all of this data, what we need to do, we need to find probability of X given IMU, lidar, wheel, camera. This is kind of fusing as well. So with knowing just Bayesian methods and Bayesian inference, you can combine all of those knowledge just in one formula. The rest is just to maximize this, or argmax, find X. That's what we do. So instead of knowing, for example, how Kalman filter works, you just can do this and make Kalman filter much better than Kalman filter. You can make we can factorize this. You can factorize this. You can see this based on what we learned, chain rule and whatever. We can factorize this to the pieces, and then that's maximization. You can get log from that, or minus log to make max mean, become minimized, and all of this multiplication becomes addition, and all of those exponential families becomes just exponent. Exponent get out, and becomes linear. You can solve it in a linear time. You can see that later soon. That's the amazing part of Bayesian inference. So this is called inference. When you use Bayesian method for that, it's called Bayesian inference. Let's clean this up to go one step forward. So inference means combining prior knowledge plus or belief. Prior knowledge is belief, actually. Prior knowledge is belief. And sensor data, add them together to update or belief. So this is how it works. And it can be used for localization, it can be used for mapping, it can be used for tracking. Tracking is also another thing. Tracking means you have an observer that watching something, and that means tracking. But localization means observer need to get localized. And mapping means not just observer, but also all of landmarkings need to get positioned and find a position. And at the end, we're going to have a map of all environment that to make that precise, we need to make a loop. We need to have a loop closure to fix everything together. If you want to make a proper map. So for example, robot moving in an environment that is unknown and suddenly see a door here. So consider that as one of the part and moving this part and this part. And then coming back and see that door again and say, oh, okay, connect everything together. That becomes a map. This is called a SLAM. A SLAM works based on that. Okay, we're going to see that later soon. So, yes, as I said, modern robotics means probabilistic inference. And SLAM, filtering, state estimation, sensor fusion, and prediction all become. Let's talk about the SLAM a little bit. Very small example here. We have a robot that, for example, imagine there is, first of all, SLAM is simultaneous localization. Localization and mapping. It means robot doesn't know anything about environment, but at the same time can find landmarkings. What is landmarkings? Landmarkings are some specific things that can be used for localizing itself based off them, like walls, doors, edges, for example, window, whatever. You know, in a street, so many things can be used as a landmarking. And based off this landmarking, for example, the position was pose 1, and there is 2 landmarkings. Based off distance to those landmarking, you can estimate your position based off those. And you can, because they make triangle. And with triangle, you can estimate relationship between these triangle edges, and you can find the next position based on. But this is all belief. This is all belief because it's not precise. Your cameras has noise, everything. Sensors are not precise. So to correct them, we need to make a loop at the end. But this is called a SLAM. So a SLAM is actually estimating 2 things. Not just your position, but also landmarking positions. You are detecting both of them at the same time with the same algorithm. So we are moving from x1, x2 to x3, and we observe 2 landmarking, for example, L1 and L2, and we have some sensors. And based off those sensors, for example, we can say distance of us to the landmarking is this much, based off, for example, some bearing and LIDAR, for example, we can get those distance. And we can, the goal is to detect position of robot and also landmarking locations. This is called a SLAM. Any question? Okay, so, and everything is uncertain. They are not precise. We we need sometimes do some assumption. For example, most of the time we assume uncertainty is Gaussian. When we have, for example, when we say, okay, the robot is here, but we have some Gaussian noise, means we have an ellipse around this robot that we don't know exactly which part of, we are considering the center, but it can be anywhere in that ellipse or circle sometimes. If there is correlation, it makes it ellipse. If it's not correlation, it's right, it's circle. So that's called Gaussian. Most of the time, Gaussian assumption is the simplest assumption because Gaussian is exponential, and exponential families are the best things that in terms of optimization you can have. So real world is noisy. Sensors, actuators, environment, all of them. And you actually, and probability distribution tell us how confident we are about every position that we have. So confidence coming from probability distribution. Probability distribution in continuous time is called PDF, like for example Gaussian, or a PMF is for discrete time. But we don't care about that part. And what we want to find we want to find the states. We want to find the state, and a state is not always one variable, it can be a vector. When you have, for example, x and y, d of x, d of y, d2x, x2d, for example, like this, if you want to also work with acceleration or jerk, you can use that. So that's our belief, so we need to find that. We also, because it's probability, we need to add up to 1. That's another point that we need to normalize it. And measurements give us the likelihood, and the Bayesian rule give us posterior. So P of x given z called posterior density. Posterior density. So anytime when I said posterior means P of x given measurements. When I said z, it can be so many other measurements here. It can be fused together. Regarding z, we don't have exact values. We have the likelihood of measurements. That's still probability. Anytime is anything related to measurements called likelihood. Anything regarding to unknown value or hypothesis called posterior. This is just some expressions that we use in probability. Okay, so let's see what else we have. So I already explained this, posterior distribution. So the posterior distribution means belief after seeing all measurements. After seeing all measurements. And as I said, it doesn't matter to the P of Z, because that's not, it doesn't have X, doesn't have X. And this means proportion. Proportion means in optimization, we just look at proportion. Proportion is very important. We don't need to consider so many other things. We remove things out. We don't need to, even though we are probability, but here, even they add up to something higher than 1, we don't care, because we want to optimize it. We want to find maximum or minimum of that. So that's also, we already talked about it. This is prior, and this is likelihood, that we already talked about that. And what we want to find, we want to maximize P of x given z. P of x given z. When I'm talking about the max, actually is argmax because we want to find x star. X star is the optimal x. So this is actually the basic of Bayesian inference, finding that x. That's called Bayesian inference. Whatever I talk about using Bayesian rules, break down the problem to some prior and likelihood, and then get max, argmax. Argmax means find the argument. With maximizing this, find x. And this is Bayesian inference. That's a basic for SLAM, for tracking, for filtering. That's all based off that. Okay, I think next class we're going to talk about, okay, right now we didn't talk about them actually graphical method. We can make it even very nicer to understand with graphical models. We're going to talk about that next class.